All right. As you can tell, my day's basically fucked. I got started really late today, but I am getting started. I took a nap here. I think it's like maybe 45 minutes. Uh, 1:15 maybe. This is just, go back there. Why does it do that? Why does it do that? Piece of shit. You have to click save. All right. Lab. What is it? Lab. Nap. 1:15. This is the worst calendar software ever. All right. I had to go grocery shopping. Can I not just update this one? Oh, it's so fucking annoying. Anyways, I had to go grocery shopping and I didn't have time to uh, do my cardio in the beginning of the lunch cardio session. So I went grocery shopping, prepared my lunch, ate it, fell into a glucose coma, woke up, did my cardio. Which took about 30 minutes. And then I can mark this thing as what? Dark purple. And to be honest, like a lot of this was like, yeah, anyways, I'm not gonna discard, please. Bullshit. Admin bullshit. There we go. All right, and that puts us here where we're at today, with only 2.5 hours, less than that, to get any progress done. I'm so upset because it's like I had a good start today. I woke up super early. I got up around like 4:15, and I got an early start to the day. My day started really well. I got to the gym early. I was able to warm up really great. I did all the warm up stuff. I did some, I went through all the exercises in my exercise program before my coach even showed up to the gym. So I was like really prepared for the workout. Did the workout, felt great. Coming home, I did burn some time during this like shower breakfast thing. One thing I do need to fix here is that like this actually only takes me about like 15 minutes to drive to the gym. I do like leaving early though because I get to the gym early. So maybe I'll continue to do that. But driving home definitely only takes about 15 minutes. But sometimes my workouts run long, so I'll leave it the way it is, the blocking. All right, so yeah, I got a good start today, and then I had this APOD meeting. I burned some time in the morning waiting around for this APOD meeting to start. APOD meeting went well. And then, yeah, just when lunch hit, having to go grocery shopping and do all that stuff just kind of sidetracked me. So I think what I'm going to do today is I'm going to squeeze in a couple extra hours in the evening. This event. And can I do like a copy? Is this thing copy? Duplicate event, yes. But I want to do it today. Yeah. So at least I get a couple more hours in after dinner. Yeah. Okay. I'm gonna go ahead and get started on the reading here. Sorry, I wanted to, before I start reading, I want to start taking a picture of where I'm at for my accountability pod. Here we go. Clean the camera off here. That is so stupid that they do that. I hate technology. I hate computers. I hate devices sometimes. I love computing. I love machines and producing software that it works, that is robust, that is reliable, that is secure, that is thought through carefully. And so much software in this world is just complete fucking garbage. That is really what I'm speaking to when I say I hate computers. I hate all of the shitty fucking software that's out there that's produced with zero thought. And AI, this was before AI. AI is just making it worse. Yeah, this Signal app. I took a photo, and then I go to edit the photo to rotate it because for some reason the camera can't get that when I'm in portrait mode and I take a photo that it should put the photo in portrait mode. So I go in, it's like lopsided this way, and so I go into Signal before I send the message, and I click rotate, and it can only rotate at one direction. It can't rotate at the other direction, so you have to go full 270 degree rotation, and then I send it, and it sends not only the rotated image but also the original. It's like, why did you do that? Who thought that was a good idea? And then there's no way in Signal to just go in and select one image of your message and delete that. You can delete messages in Signal, but you can't delete just one image if there's two images in there. Can't do that. Really? I mean, in this day and age with all this AI stuff, we can't like just produce really high quality software that is intuitive, that just does what you want it to do. All right, rant over. I need to study here. All right, let me get my water bottle And I'm going to turn the AC on, and then I'll turn the light on, and then I'll get started studying here. Okay, we are on enhancing parallelism. We do get status on here. We are clear. All right, enhancing parallelism. At this point, our functions have hit a bounds imposed by the latencies of our arithmetic units. As we have noticed, however, the functional units performing addition and multiplication are all fully pipelined, meaning that they can start new operations every clock cycle, and some of their operations can be performed by multiple functional units. The hardware has the potential to perform multiplications and additions at a much higher rate, but our code cannot take advantage of this capability. Even with loop unrolling, since we are accumulating the value as a single variable accumulator, we cannot compute a new value for accumulator until the preceding computation is completed. Even though the functional unit computing a new value for accumulator can start a new operation every clock cycle, it will only start one every L cycles, where L is the latency of the combining operation. We will now investigate ways to break this sequential dependency and get better performance than latency bound. So obviously this next section is about multiple accumulators, and what I'm going to propose up front before reading this is that when you have that single accumulator, you have a data dependency that limits the inherent parallelism of the computation. When you split it out into multiple accumulators, you might think, well, it's a single thread, it's running on a single core, it should run pretty much the same thing. But there's all this, what they refer to as instruction level parallelism. And this is parallelism inherent in your algorithm, in the expression of your computation, that the CPU enables into your program. Even though your program is a sequential series of instructions, this instruction level parallelism is enabled by the CPU, where the CPU will actually be doing work in parallel, in true parallel form, because it can determine that your instruction sequences are independent of each other. So what we're going to do is we're going to accumulate into one accumulator half the work, and then another accumulator the other half the work. At the very end, we're going to do a join. And it might think like, oh, if it's done in a single thread, like why would you do half the work on one accumulator? Like, it's because of this instruction level parallelism. You want it to be able to take advantage of it, and make it easier for the CPU to be able to detect the instruction level parallelism. For a combining operation that is associative and commutative, such as integer addition and multiplication, we can improve performance by splitting the set of combining operations into two or more parts and combining the results at the end. For example, let P denote the product of elements A0 through n-1. Okay. Pn denote the product of elements A0. Okay, so Pn is equal to the product for I. Yeah, okay, exactly. Assuming n is even, we can also write this as Pn is Pe n times Pon, where En is the even elements and O is odd elements. Yep. Okay. Figure 521 shows code that uses this method. It uses both two-way loop unrolling to combine more elements per iteration and two-way parallelism, accumulating elements with even indices in variable accumulator 0 and elements with odd indices in variable accumulator 1. We therefore refer to this as 2 times 2 loop unrolling. As before, we include a second loop to accumulate any remaining array elements for the case where the vector length is not a multiple of 2. We then apply combining operations to accumulator 0, accumulator 1 to compute the final result. Comparing loop unrolling alone to loop unrolling with two-way parallelism, we obtain the following performance. So this is actually going to be a significant performance improvement. Yeah. And you can see we just use two separate accumulators. So perform these operations are completely independent. So it's a read of memory. I mean, they're dependent in a way, how do I say this? In they call it false sharing sort of way, but it works in our advantage in that we're going to be reading in order. So we're going to be reading from the same cache lines, same cache lines. So we do a fetch from memory, and then we do some arithmetic operation on that, and we store it in accumulator 0, and then I+1, different memory location, different accumulator. And these can be on stack or they can be in registers. But either way, I mean, they're probably going to be stored in registers. But either way, they're completely independent operations. They can be ran out of order. They can be ran at the same time if the functional units allow it to be ran at the same time. I don't think they need to be pipelined, to be honest. Perhaps they're pipelined as well. But the CPU might be able to do some really smart things. I don't know. But it might be able to do some really smart things where it sees that there's no dependencies between these operations and just performs them entirely in parallel. Okay, we see that we have improved the performance for all cases with integer product, floating point addition, floating point multiplication improving by a factor of around 2, and integer addition improving by somewhat as well. Most significantly, we have broken through the barrier posed by the latency bound. The processor no longer needs to delay the start of one sum or product operation until the previous one is completed. To understand the performance of combined 6, we start with the code and operation sequence shown in figure 522. Okay. We can derive a template showing the data dependencies between iterations through the process shown in figure 523. As with combined 5, the inner loop contains 2 multiplication operations, but these instructions translate into mul operations that read and write separate registers with no data dependency between them. We then replicate this template n divided by 2 times, modeling the execution of the function on a vector of length n. We see that we now have 2 critical paths, one corresponding to computing the product of even number elements, program value accumulator 0, and one for the odd number elements with accumulator 1. So let's just look at these graphs here. So he likes doing these graphs. I mean, they're handy. Why does this load perform before the add? I would think it'd be like this. Huh. Okay. With the odd number elements, yeah, okay. Each of these critical paths contains only n divided by 2 operations, thus leading to a CPE of around 5 divided by 2 at 2.5. A similar analysis explains our observed CPE of around L divided by 2 for operations with latency L for the different combinations of data type and combining operations. Operationally, the programs are exploiting the capabilities of functional units to increase their utilization by a factor of 2. The only exception is for integer addition. We have reduced the CPU to below 1, CPU to below 1, but there is still too much loop overhead to achieve a theoretical limit of 0.5. We can generalize the multiple accumulator transformation to unroll the loop by factor of k and accumulate k values in parallel, yielding a k times k loop unrolling. Figure 525 demonstrates this effect of applying this transformation of values up to k equals 10. We can see that for sufficiently large values of k, the program can achieve nearly the throughput bounds for all cases. Integer addition achieves a CP of 5.4 with k is equal to 7, close to the throughput bound of 0.5, and caused by the 2 load units. Integer multiplication floating point addition achieves CPs of 1.01 when k is greater than 3, approaching the throughput bound of 1 set by their functional units. Floating point multiplication achieves a CP of 0.51 for k is greater than or equal to 10, approaching the throughput bound of 0.5 set by the 2 floating point multipliers and the 2 load units. It is worth noting that our code is able to achieve nearly twice the throughput with floating point multiplication as it can with floating point addition, even though multiplication is a more complex operation. In general, a program can achieve the throughput bound for an operation only when it can keep the pipelines filled for all the function units capable of performing that operation. For an operation with latency L and capacity C, this requires an unrolling factor K greater than C times L. For example, floating point multiplication has C2 and L5, necessitating an unrolling factor of K greater than or equals 10. Floating point addition, let me see that. Where's floating point? Okay, yeah, here. Where's the diamonds at? I guess the diamonds are hiding behind here. Or no, these are diamonds and these are squares. Okay. Floating point addition has C1 and L3, achieving a maximum throughput with K. Floating point addition of 3. Yeah, looks like that worked. In performing the K times K unrolling transformation, we must consider whether it preserves the functionality of the original function. We've seen in Chapter 2 that 2's complement arithmetic is commutative associative when the overflow occurs. Hence, for an integer data type, the result computed by combined 6 will be identical to that computed by combined 5 under all possible conditions. Thus, an optimizing compiler could potentially convert the code shown in combined 4 first in a two-way unrolled variant of combined 5 by loop unrolling, and then by that of combined 6 by introducing parallelism. Some compilers do either this or similar transformations to improve performance for integer data. The big idea here that I think I'm starting to understand is that parallelism in code is not limited by multi-core or by running on something like a hardware accelerator. Like, you can have parallel computation, not even from symmetric multithreading, but from leveraging the parallelism built into an individual CPU core. I'm kind of curious now, like, would under a symmetric multi-threaded model where you have a single core that has, like, say, 2 hardware threads, or what do they call them, hyperthreads, would you, if you had workloads that were fully leveraging their instruction level parallelism of that chip, would they interfere with each other? Or could you have them, because I think hyperthreads, SMT, I think they share functional units. That is my understanding. So I think you might run into situations where if you're fully leveraging that hyperthread's functional units, you might be like a noisy neighbor with the other workload that's running on the other side of the core. But yeah, coming back to what I was saying before I took a break here, is just that you can write your code in such a way that even though you're not using any fancy concurrency, multi-threaded, accelerated parallel computing constructs, you're just writing normal C code, you can write it in a way sometimes that it has inherent parallelism obvious to the CPU, that it can then take advantage of this instruction level parallelism really well. Okay. On the other hand, floating point multiplication and addition are not as associatives. Thus, combined 5 and combined 6 could produce different results due to the rounding or an overflow. Imagine, for example, a product computation in which all of the elements with even indices are numbers with very large absolute values, while those with odd indices are very close to 0. In such a case, product PEN might overflow, or PON might underflow, even though computing product PN proceeds normally. In most real-life applications, however, such patterns are unlikely, since most physical phenomena are continuous. Numerical data tend to be reasonably smooth and well-behaved, even when there are discontinuities. They do not generally cause periodic patterns that lead to a condition such as that sketched earlier. It is unlikely that multiplying the elements in strict order gives fundamentally better accuracy than does multiplying two groups independently and then multiplying those products together. For most applications, achieving a performance gain of 2x outweighs the risk of generating different results for strange data patterns. Nevertheless, a program developer should check with potential users to see if there are particular conditions that may cause the revised algorithm to be unacceptable. Most compilers do not attempt such transformations with floating point code, since they may have no way to judge the risks of introducing transformations that can change the program behavior no matter how small. Cool. So we're catching up here. Reassociation transformation. We now explore another way to break the sequential dependency and therefore improve performance beyond the latency bound. We saw that the k times 1 loop unrolling of combined 5 did not change the set of operations performed in combining the vector elements to form their sum product. By a very small change in the code, however, we can fundamentally change how many the way the combining is performed, and also greatly increase the program performance. Figure 526, which is some code on the next page, shows a function combined 7 that differs from the unrolled of combined 5 only in a way that the elements are combined in the inner loop. In combined 5, the combining is performed by the statement. Okay, so we just changed the associativity of the expression, differing only how the two parentheses are placed. We call this a reassociation transformation, because the parentheses shift the order in which the vector elements are combined with an accumulated value ACC, yielding a form of loop unrolling referred to as 2 times 1a. To the untrained eye, the two statements may seem essentially the same, but when we measure the CPU, we get surprising results. So let's look at the code before we look at the results. So again, op and data t, these are not defined. So the data t destination and vector, say get vec start, The thing I really like about C is that it's so fucking obvious what's going on. Like some languages, you read an expression and you're like, this could literally do anything. Like with operator overloading. Operator overloading, I'm not too. I guess I'm not too much critical of, but dynamically typed languages, especially like Ruby and Python, especially Ruby, where you can have like method undefined. I forget what like in Python there's like a get adder dunder method, I think it's called, that allows you to just kind of like create a method on the fly, but a method is still accessed on the object itself. Whereas in Ruby, since everything's a method, you can have just an expression that looks like a function call, but it ends up being dynamically generated at runtime. It's just like, it can do anything. Whereas with C, you look at it, it's like, okay, you can work through it in your head, and it's pretty obvious, pretty fucking obvious what's going on. I think with pound defines, like they pound defined this vector pointer to just be like a vec pointer. So you have to like constantly be like looking up how these things are defined. But once you understand how things are defined and the type defs, the pound defines, any macros, once you understand that stuff, that's about all the magic there is to see. Everything else is pretty straightforward. Anyways, we're going through here and looking at the associativity transformation. So the first one was where they had the accumulator op data and then performed that op with the data. The last one was look up both of the datas and perform the op. And then perform that op against the accumulator. Interesting. I wouldn't think that would be faster, but we'll find out why it is. To an untrained eye, two statements may seem essentially the same, but when we measure the CPU, we get surprising results. This will be 2 times 1a unrolling. So in the multiplication and floating point operations, they're about cut in half, which is really good. The integer addition case matches the performance of k times 1 unrolling, while the other 3 cases match performance of the versions of parallel accumulators. Does it? Yeah, it does. Doubling the performance relative to k times 1 unrolling. These cases have broken through the barrier imposed by the latency bound. Figure 5 to 7 illustrates how the code for the inner loop of combined 7, for the case of multiplication as a combining operation and double as a data type, gets decoded into operations that result in data dependencies. We see that the load operations result from the vmove sd and the first vmove sd instruction load vector elements I and I plus 1 from memory. The first mul operation multiplies them together. The second mul operation multiplies this result by the accumulated value of ACC, figure 528A. Oh, it's this little diagram thing, okay. Shows how we rearrange, refine, and abstract operations in figure 527 to get a template representing the data dependencies for one iteration. As with templates for combine 5, combine 7, we have to load 2 mul operations, but only one of the mul operations from the data dependency chain between loop registers. When we replicate this in template n divided by 2 times to show the computations performed in multiplying n vector elements, we see that we only have n divided by 2 operations along with the critical path. The first multiplication within each iteration can be performed without waiting for the cumulative value from the previous iteration. Thus, we reduce the minimum possible CPU by a factor of around 2. Okay. I'm not sure I fully understand that. Okie. So we got a couple more pages here, practice problem that I'm going to skip, and then we have our Cindy website. We get to profiling at the end of this chapter, which I'm excited for. Okay. Figure 530 demonstrates the effect of applying the reassociation transformation to achieve what we refer to as k times 1 loop unrolling, where I use up to k10. Okay. You can see that this transformation yields performance results similar to what is achieved by maintaining k separate accumulators with k times k unrolling. In all cases, we come close to the throughput bounds imposed by the functional units. In performing the reassociation transformation, we once again change the order in which the vector elements will be combined together for integer addition and multiplication. The fact that these operations associated implies that this reordering will have no effect on the result. For the floating point cases, we must once again assess whether the reassociation is likely to significantly affect the outcome. We would argue that the difference would be immaterial for most applications. In summary, the reassociation transformation can reduce the number of operations among the critical path in computation, resulting in better performance by better utilization of utilizing the multiple functional units and their pipelining capabilities. Most compilers will not attempt any reassociations of floating point operations, since these operations are not guaranteed to be associative. Current versions of GCC do perform reassociation of integer operations, but not always with good effects. In general, we have found that unrolling a loop and accumulating multiple values in parallel is a more reliable way to achieve improved program performance. Consider the following function for computing the product of an array of n double precision numbers. We have unrolled the loop by factor of 3. For the line labeled product computation, we use the parentheses to create 5 different associations with the computations as shown. Assume we run these functions on a machine where floating point multiplication has latency of 5 clock cycles. Determine the lower bound. I don't want to do this. Skip. 5.8 is going to be a skip. Problems. Okay, now we're in the website. And we go down here to SIMD. It's kind of freaking me out here that they have a copy of the text, but it's different sometimes. As described in section 3.1, Intel introduced the SC extension SC instructions in 1990, where the SC is the acronym for Streaming SIMD Extensions, and in turn, SIMD, pronounced SIMD, is the acronym for Single Instruction Multiple Data. More recent versions of the x86 processor employ AVX multimedia instructions. The SC capability has gone through multiple generations, with more recent versions being named Advanced Vector Extensions, or AVX. The SIMD execution model involves operating on entire vectors of data within a single instruction. Yeah, I feel like I need to just read both of these because they're different texts. They start off similar, but they're very different. Okay. The SIMD execution model involves operating on entire vectors of data within single instructions. These vectors are held in a special set of vector registers named YMM0 to YMM or ZMM now. Current AVX vector registers are 32 bytes long, and therefore can hold 8 32-bit numbers or 4 64-bit numbers, where the numbers can be either integer or floating point values. AVX instructions can then perform vector operations on these registers, such as adding or multiplying 8 or 4 sets of values in parallel. For example, if YMM register YM0 contains 8 single precision floating point numbers, which would denote A0 through A7, and RCX contains the memory address of a sequence of 8 single precision floating point numbers, which we denote B0 to B7, then the instruction dereference of RCS to YMM0 and YMM1. How does that work? Or it says multiply RCS stuff by YMM0 and store in YMM1. We'll read 8 of the values from memory and perform 8 multiplications of parallel computing AI times BI, and it stores in YMM1 though. And storing the result in 8 product vectors in a vector register YMM1. So then why do they say it goes to AI? It should be whatever. We see that a single instruction is able to generate a computation over multiple data values, hence the term SIMD. GCC supports extensions to C language that let programmers express a program in terms of vector operations that can be compiled into vector instructions of AVX, as well as code based on the earlier SSE instructions. This code style is preferable to writing code directly in assembly language, since GCC can also generate code for the vector instructions found on other processors. Using a combination of GCC instructions, loop unrolling, and multiple accumulators, we are able to achieve the following performance of our combining functions. What? So vector 8x8, vector throughput bound. This chart, the first set of numbers is for conventional scalar code written on this style of combined 6, unrolling by a factor of 10 and maintaining 10 accumulators. Second set of numbers is for code written in the form that GCC can compile into AVX vector code. In addition to using vector operations, this version unrolls the main loop by a factor of 8 and maintains 8 separate vector accumulators. We show the results for both 32-bit and 64-bit numbers. Does it? I don't see that. Oh, int and long. Okay. Since the vector instructions achieve 8-way parallelism in the first case, but only 4-way parallelism in the second. That makes sense. We can see the vector code achieves almost an 8-fold improvement on our 4 32-bit cases and a 4-fold improvement on 3 of the 4 64-bit cases. Only the long integer multiplication code does not perform well when we attempt to express it in vector code. The AVX instruction set does not include one to do parallel multiplications for 64-bit integers, and so GCC cannot generate vector code for this case. Using vector instructions creates a new throughput bound for the combining operations. These are 8 times lower for 32-bit operations, 4 times lower for 64-bit operations than the scalar limits. Our code comes close to achieving these bounds for several combinations of data type and operations. Our presentation is based on AVX2, so we're on AVX 512 on this machine. The second version of AVX introduced with the Core i7 Haswell processor in 2013. GCC will generate AVX2 code when given the command line parameter mavx-2. We will show how the SIMD instructions can be used to implement vector computations where multiple data values are computed in a single operation. The idea behind SIMD execution model in AVX2 is that each 32-byte YYM register can hold multiple values. In our example, we will consider the case where they can hold either 8 integer or single precision values or 4 double precision values. AVX2 instructions can then perform vector operations on these registers, such as adding or multiplying 8 or 4 sets of values in parallel. For example, if YMM register YMN0 contains 8 single precision floating point numbers, which we've denoted A0 through A7, and RCX contains a memory address that, I already read this. GC supports extensions to the C language that I already talked about that. Writing in C also has advantage. GC will generate scalar code for a machine. Okay, we already said that. We will describe how to write code using the GCC support for vector operations using our combining functions as examples. The basic strategy is to define a vector data type vect that holds either 4-byte values or 4 8-byte values. 8 4-byte values or 4 8-byte values. If we have 2 such vectors, VA and VB, then the expression VA times VB causes a SIMD multiplication of the vector elements. Okay. Let's look at the code. Our first step is to declare the vector data type. Since we're trying to make the same code work for base data types int, long, float, and double, we'll use a combination of type def declarations and constant definitions to make code more general. As with our earlier versions, we assume that the base data type has been declared as type data t. We define v bytes to be the number of bytes in a vector. For AVX2, this is defined to be 32. So I would have 64, I think. But we would like to keep this value parameterized to easily adapt the code for other machines. We then define v size to be the number of elements in each vector, which, yeah, okay, makes sense. We are now ready to define the vector data type. This involves a notation that is idiosyncratic to GCC. So we say type def data t vect, what? Attribute, what the fuck is this shit? So how do I parse this? So I think you're just redeclaring data t to be a vect. And then there's this custom thing that where it uses underscore attribute, the dunder attribute thing. This declaration states that the data type of vect is vector, where the elements are of type data t. And the vector consists of v bytes. Elements of a vector can be referenced using array notation. For example, the following code initializes a vector element to the combining code's identity element. Declare vector initialize elements to identity. So you say vect accumulator, and we go up to v size. Say, hey, put in the identity to the accumulator. Okay. The following shows a simple example of computing the inner product of two SIMD vectors. So you have AV and BV as two vectors. We declare a long int I. Can you just call that a long? You don't have to call it a long int. Vect PV is the product of AV times BV. And then we have a data T result is equal to 0. And we go over every element of PV and we add up the result into the final result. Okay. In this code, the multiplication operation on line 4 multiplies the corresponding elements of vector AV and BV. The code on line 7 acts as an element of the product vector with the overall loop combining the sum of the elements. All right. Alignment requirements. Some of the AVX2 instructions impose a very strict alignment requirement on memory operands. They require that any data being read from memory into an YMM register or written from a YMM register to memory satisfy 32-byte alignment. An instruction that attempts to read or write unaligned data can cause a segmentation fault. Wow. Indicating an invalid memory reference. This alignment requirement will factor into how we write programs that make use of AVX2 instructions. There are AVX2 instructions that can access unaligned data, but early implementations were not very efficient, so GC does not currently generate code that uses them. Implementation of combining functions. Analysis. And then problem sets. Okay. Figure 1 shows the code for a combining function that makes use of the SIMD operations. The overall idea is to set up a vector variable accumulator that accumulates either 8 data types int and float or 4 data type double values in parallel. The code starts by initializing the accumulators to the identity elements using array indexing to set the individual elements of the vector. To satisfy the alignment requirement, we need to accumulate several vector elements using scalar operations. To satisfy the alignment requirement, we may need to accumulate several vector elements using scalar operations until the remaining data has an address that is multiple of v bytes. The code for this is shown at lines 14 to 17. Observe, we cast pointer data to data type size t so we could test whether it is multiple of v bytes. You must also keep track of the number of remaining elements count and consider the case where count is smaller than the number of elements in a single vector. Okay. I think I remember reading through this code before. So we initialize all accumulated entries to the identity. We single step until we have memory alignment. Which we have our data pointer that we're going to advance. But we also is plus plus higher precedence than star? I would think dereferencing would be. Let's see. C operator precedence. Star as a unary operator, and then plus plus the right to left associativity. What the fuck? Everything's left to right except for unary operators are right to left. All of them? I knew some of them were like that, but wow, okay. And then ternary conditional operators right to left. Assignment operators, comma. No, just assignment. Okay. So this thing happens first, but it's a post increment, which means that the value that's returned from this is not affected by that, and then we dereference it. But the actual value there will be mutated and advanced by one element. Okay, I can see how this would get us to a point where our data pointer is aligned. But what do we do with the results between... Where's data at? Yeah, it's the start of the vector. So you can't, how do you handle those elements? Well, so we cast that into a chunk, which is a vec_t, and then we accumulate that into another vec_t using this operation. And then we advance our data and we subtract our count. So we built up this. Wait a minute, what? Our count is our vector length. Oh, it's performing the operations one at a time. Okay. So we don't have to worry about dealing with them later. Makes sense. Okay. Single step through the remaining elements. So we just go until count no longer is positive. This is one of the situations where I prefer to have it says while count is greater than 0, because if you happen to go negative, you want to catch that. Combine elements of accumulator vector. Yeah, and then you just say result op accumulator I. Yeah, for v size. Yep, all that makes sense to me. Lines 20 to 25 show the main loop of the function here. So we see here the use of casting to create a pointer to a vector having the same address as a pointer to data. Dereferencing this pointer then retrieves an entire vector of data from memory, defined here by vector variable chunk. The statement accumulator is equal to accumulator op chunk then combines the vector values read from memory with the values in the parallel accumulators. In the event that the main loop terminates before all values have been accumulated, we have another loop to single step through the remaining elements. So you could have a non-vector sized array, or how would I say this? A non-SIMD vector T sized vector of data. So you have all the stuff at the beginning to get to the alignment point, and then you have your chunks of your vector that you're processing, and then you have everything else after that that doesn't fit within a chunk. Analysis. The following table shows the results for code figure 1 compared to the best method using only scalar operations. So we can just massively outperform. Oh wait, scalar 10 by 10. What? So scalar 10 by 10 outperforms vector 1 by 1? I wouldn't think that for long addition and long multiplication. I guess because the longs are really big. But even for multiplication on the integer, a 32-bit integer, it still doesn't outperform it. For floats, it outperforms, again, 32-bit addition and 64-bit addition, but not multiplication. Note we now list the performance for the different integer sizes and the different floating point sizes separately. Although these two cases have identical performance for scalar code, they have different performance with vector code, since one achieves 8-way parallelism while the other just 4-way. We see that the resulting performance is a bit mixed. For integer addition and both single precision addition and multiplication, we have broken through the barrier that we have seen for scalar implementations. On the other hand, other operations did not perform as well as we achieved using scalar code. Fortunately, we can combine our earlier techniques for further enhancing parallelism, either by expanding the number of accumulators or by using reassociation, yielding the following performance. So vector 8 by 1a or 8 by 8 generally just beats the, no, it doesn't win on long multiplication. Everything else seems to be, well, I guess, yeah. Yeah, it's still kind of mixed. I mean, it's better. Doesn't beat the crap out of scalar, though. We can see the vector code achieves almost an 8-fold improvement on the 4 32-bit cases and a 4-fold improvement of the 4 64-bit cases. Only the long integer multiplication code does not perform well when we attempt to express in vector code. The AVX instruction set does not include one to do parallel multiplication of 64-bit integers, and so GC cannot generate vector code for this case. Using vector instructions creates a new throughput bound for the combining operations. These are 8 times lower for 32-bit operations, 4 times lower for 64-bit operations than the scalar limits. Our code comes close to achieving these bounds for several combinations of data types and operations. Alright, bunch of problems and then some solutions. I really don't want to do these problems. Yeah, I'm gonna skip these problems. Boop. I'm just not in a problem solving mode. I like SIMD stuff, but read me. How did I even do that? Okay. It's a really boring introduction to SIMD. I guess, I was looking forward to doing some SIMD in this website, but they only use one feature of GCC, which is that like vector attribute thing. And it's all caught up in their freaking combine function. I feel like if I want to do more SIMD stuff, I'll just do it during the course that I'm taking later this quarter. This parallel computing course. It is nice to get a little bit of exposure to it, but like if all it is a GCC attribute, it's like, okay, I don't really want to even like spend time doing that. Because it's basically you just treat it like a vector that you perform operations on, and the compiler creates all the SIMD instructions for you. It's like nothing surprising there, I would say. And we're not really solving a problem. We're just toying around with like this combine function, which is completely synthetic. I want to do something where I actually solve a problem with it, which I think the parallel computing course I actually will. So I'll just skip those for now. All right, next section, summary of results. Let's close this out. For optimizing combining code, our efforts at maximizing performance of a routine that adds or multiplies elements of vector have clearly paid off. Following summarizes the results we obtained with scalar code, not making use of vector parallelism provided by AVX vector instructions. Great. By using multiple operations, we have been able to achieve CPEs close to the throughput bounds of 0.5 and 1.0, limited only by the capabilities of functional units. These represent 10 to 20 times improvements on the original code. This has all been done using ordinary C code and a standard compiler. Rewriting the code to take advantage of fewer SIMD instructions yields additional performance gains of nearly 4x or 8x. For example, for a single precision multiplication, a CPE drops from the original value of 11.4 down to 0.06, an overall performance gain of over 180x. This example demonstrates that modern processors have considerable amounts of computing power, but we may need to coax this power out of them by writing our programs in very stylized ways. Some limiting factors. Register splitting, branch prediction and misprediction penalties, we've seen that the critical path in a data flow graph representation of a program indicates a fundamental lower bound on the time required to execute a program. That is, if there is some change of data dependencies in a program where the sum of all the latencies along the chain equals t, the program will require at least t cycles to execute. We have also seen that throughput bounds of the functional units also impose a lower bound on the execution time of your program. That is, assume that a program requires a total of n computations of some operation, that the microprocessor has c functional units capable of performing that operation, and that these units have an issue time of I. Then the program requires at least n times I divided by c cycles to execute. In this section, we will consider some other factors that limit the performance of programs to actual machines. Register spilling. I've never heard of this term before. The benefits of loop parallelism are limited by the ability to express computations in assembly code. If a program has a degree of parallelism p that exceeds the number of available registers, then the compiler will resort to spilling, storing some of the temporary values in memory, typically by allocating space on the runtime stack. As an example, the following measurements compare the results of extended the multiple accumulator scheme of combined 6 to the case of K10 and K20. So performance actually got worse in every situation. You can see that none of the CPUs improved with this increasing amount of unrolling, and some even got worse. Modern x86 64 processors have 16 integer registers and can make use of the 16 YYM registers to store floating point data. Once a number of loop variables exceeds the number of available registers, the program must allocate some on the stack. As an example, I wonder, can you store just integer data in YYM registers? Or ZZM? It's SKI. Can you store just regular integer data in YM, or we say XMM, YM, ZMM registers? If so, can you operate on them on integer as vectors using AVX instructions? Imagine you can. Okay. I wonder why the book said why I merged is to store floating point data. Maybe that's just a GCC convention. If this is the case, why then does GCC not use these registers more often for integer data? say can GCC use X, Y, Z, MM registers to store scalar data and operate on those registers with normal operations, not SIMD. It has scalar floating point, but it doesn't have scalar integer. Okay. And returns. Okie dokie. Modern x86 processors have 16 integer registers and can make use of the 16 YIM registers to store floating point data. Once the number of loop variables exceeds the number of available registers, the program must allocate some space on the stack. As an example, the following snippet of code shows how accumulator AC0 is updated in the inner loop of the code with 10x10 unrolling. Updating accumulator AC0 and 10x10 unrolling. So there's a vmult SD RDX times RDX dereferenced times XMM0 stored in XMM0. You can see that the accumulator is kept in register XMM0, and so the program can't simply read data I from memory and multiply it by its register. The comparable part of the code for 2020 unrolling has a much different form because it has to shuffle XM0 because there's only 16 AVX registers. The accumulator is kept as a local variable on the stack. At offset 40 from the stack pointer, the program must read both its value and the value of data I from memory, multiplying them, and store the result back to memory. Once the compiler must resort to register spilling, any advantage of maintaining multiple accumulators will likely be lost. Fortunately, x86-64 has enough registers that most loops will become throughput limited before this occurs. Branch prediction and misprediction penalties. We demonstrated via experiments in section 366 that a conditional branch can incur a significant misprediction penalty when the branch prediction logic does not correctly anticipate whether or not a branch will be taken. Now that we have learned something about how processors operate, we can understand where this penalty arises. Modern processors work well ahead of the current executing instructions, reading new instructions from memory and decoding them to determine what operations to perform on what operands. This instruction pipelining works well as long as the instructions follow in a simple sequence. When a branch is encountered, the processor must guess which way the branch will go. For the case of a conditional jump, this means predicting whether or not the branch will be taken. When instructions such as an indirect jump, as we saw in the code to jump to an address specified by jump table entry, or procedure return, this means predicting the target address. In this discussion, we focus on conditional branches. A processor that employs speculative execution, the processor begins executing the instructions at the predicted branch target. It does this in a way that avoids modifying any actual integer register or memory location until the actual outcome has been determined. If the prediction is correct, the processor can then commit the results of the speculative executed instructions by storing them in registers or memory. If the prediction is incorrect, the processor must discard all of the speculative executed results and restart the instruction fetch process all at the correct location. The misprediction penalty is incurred in doing this because the instruction pipeline must be refilled before useful results are generated. We saw in section 366 that recent versions of x86 processor, including all processors capable of executing x86 programs, have conditional move instructions. GC can generate code that uses these instructions when compiling conditional statements and expressions rather than the more traditional realizations based on conditional transfer control. The basic idea for translating into conditional moves is to compute the values along both branches of the conditional expression or statement and then use conditional moves to select the desired value. We saw in section 457 that conditional move instructions can be implemented as part of the pipeline processing of ordinary instructions. There is no need to guess whether or not the condition will hold, and hence no penalty for guessing it correctly. How then can a C programmer make sure that branch misprediction penalties do not hamper the program's efficiency? Given the 19-cycle misprediction penalty we measured for the reference machine, the stakes are very high. There is no simple answer to this question, but the following general principles apply. So I got some principles about misprediction. Understanding memory performance is next. Low performance, store performance, some diagrams, and then life in the real world, performance improvement techniques, identifying and eliminating performance bottlenecks, program profile, and then we get to profiling, using a profile to guide optimization, and then summary. We're done with this section. Okay, what time is it? 4 p.m. I think I need to do some brilliant because my streak I don't have for today. So I think what I'll do is I'll do the brilliant when I get on in the evening after dinner. Why is this thing open? Okay, so now he's getting into SIMD stuff here. So we talked about that. We're talking about mispredictions. I'm gonna take a little break here and watch this lecture some more.
And now I'm getting it down to 1 or fewer clock cycles per element. So just as the final step is, okay, is that as good as it goes? Actually, no. You remember when I talked about floating point, I mentioned that there's this special set of registers that are on a x86 that were called XMM registers on the Shark machines. And now this Haswell, this newer generation, have something called YMM registers, which have the feature being twice as big as XMM registers. So in particular, these registers are 32 bytes long. And there's a new version coming out within a year or something. They call it AVX 512, where the register is 512 bits, so that's 256 bytes long. No, it's 512, excuse me, it's 64 bytes, right? 64 bytes, so it'll be twice as big as these. And as I mentioned before, you can think of these as a way of operating on 32 individual characters, or I can treat them as full. And now I'm getting it down that are on a x86 that were called XMM registers on the Shark machines. And now this Haswell, this newer generation, have something called YMM registers, which have the feature being twice as big as XMM registers. So in particular, these registers are 32 bytes long. And there's a new version coming out within a year or something. They call it AVX 512, where the register is 512 bits, so that's 256 bytes long. No, it's 512, excuse me, it's 64 bytes, right? 64 bytes, so it'll be twice as big as these. And as I mentioned before, you can think of these as a way of operating on 32 individual characters, or I can treat them as floating point. And we saw before that nowadays the regular floating point makes use of sort of the low order 4 or 8 bytes of these registers. But there's also instructions called vector addition, where one instruction has the effect of doing 8 floating point additions at once on float data. And on double precision, its counterpart does 4 of them at once on these. And that hardware is there. It's just sitting there waiting to use, and it seldom gets fired up to really make use of it. But so that floating point multiplier that can do floating point multiplication in 3 clock cycles and is fully pipelined can actually do 8 floating point multiplications in parallel and pipelined in 3 clock cycles. And as I mentioned, the Shark machines has an earlier version where the numbers are half of these. So it can do 4 single precision or 2 double precision at once. And if I write code that uses that, what I call vector code, then you can see I can drop by a factor of about 4 across the board here and make it run much faster. So this 0.06 is really 0.0625, right? It's doing 16 operations per clock cycle on that. Can't quite hit the vector throughput bound, but in general, making this thing run much faster. And so the people who really worry about, and you can imagine these instructions were introduced for things like video processing, image processing, sound, sort of signal processing where performance really matters. How fast you can display an image, how fast you can rotate something, how fast you can perform graphics makes a big difference. In video games are one of the big drivers, but even for sort of other operations you might do on images. And so these instructions were really designed to do it. And people who write code for those kind of applications get pretty good at writing code in a way that they can do this what's called vectorizing. And unfortunately, so the Intel compiler will actually automatically do some of this for you. GCC they attempted to implement it, and it didn't work very well, so I think they discontinued it. It turns out there's a web aside. So this is on the web from the book's web page that describes how to do this programming if you're interested. There's extensions to GCC that are very funky, really weird stuff. But you can write code that then will get compiled down to make use of these kind of instructions. And that's how I did it and how I got these performance results. OK, so that shows you if you really want to, but that's very machine specific. That will only work on, well, you can actually tune it so it's easy to compile it to go between different machines, but it's still fairly specific and very specific to GCC, in fact. So that sort of shows you, though, if you really want to push it, what you can do. Now let's get back to one of the things I told you about, how you can, if you think of your program as a very long linear sequence of instructions, then the thing is trying to grab as many of those and pull them apart as fast as it can. But of course, you know your program is actually typically a loop, and there aren't many instructions in that loop. So how is it turning that into a linear sequence? Well, that relies on an idea of how do you handle branches. So typically, the program fetching ahead, grabbing instructions, and it will come to a branch instruction, a conditional jump of some sort. And there it has a dilemma, because in general, this branch could either, be taken, meaning it will go to the branch target, or it could do what's called fall through, meaning the test fails, and so it just continues execution. And there's no way a priori to know what will happen. These can often be data dependent. And so the way this is handled on a modern processor is by doing what's known as branch prediction, which is essentially just guess. Which way is this branch going to go? Is it going to be taken or not? And you predict, and then you start executing along the predicted direction. But do it in a way that if you make a mistake, you haven't caused irreparable harm to the program. And we'll see what that means. So what really happens then is up here, there's a lot of logic that's trying to suck out instructions. And then there's a branch unit that's basically coming along later and saying, yeah, you're OK. You predicted that correctly, so you can keep going. Or it will throw up a flag and say, uh-oh, wait a minute, stop. You mispredicted this branch way back 100 clock cycles ago. Well, it's not that long ago, but some number of clock cycles ago. You've got to fix it. And so the handling of jumps then becomes more a case of guessing up here and then either confirming or denying that guess down below. So in general, then, it will predict it one way and begin executing. So imagine, for example, in a loop like I've shown you, that you predict that the branch will be taken, that you'll go back to the start of the loop again. That's actually a pretty good guess. It's a good guess until you hit the end of the loop. But let's just guess that way. And so the program will just keep guessing that the branch will be taken. And by that means, by all those guesses, basically create this long linear sequence of instructions that can be pulled in and executed. And in general, some of them will be fetched, and some of them you'll actually have done the operations that are called for in the instruction. And then what happens is if the flag goes up to say, no, this was invalid, then what will happen is it will go back and cancel all the instructions that have been fetched and executed. And the way it does that is you'll notice all these instructions only modify registers. And it has multiple copies of all the registers going back. These are the values that I'm sure of. These are sort of speculative values pending updates to them. And so when it comes time to cancel, it just cancels out all those pending updates and goes back to values that it's certain of. Question?
Where does it store the multiple copies?
There's a big block they call the register renaming unit, which is sort of multiple copies of all the registers as they get accumulated.
Why can't it store different data in the multiple copies? Like, why does it have to be the same data? Don't we potentially have more registers?
Oh, it has many more. It will typically have several hundred of these sort of virtual registers to keep pending copies to the actual registers.
So why can't it store different data?
It does. It stores, you know, here's the old value, here's the first update, here's the second update, here's the third. And it keeps track of all the, you can imagine why this is not a something you learn in a one-semester course, right? That to keep track of all those different things flying by and make sure that it works is a pretty tricky business. But conceptually, it's a pretty simple idea that it just races off, does a lot of things based purely on speculation, and then only if it makes a mistake, it goes, uh-oh, and it sort of rolls back to as if it had only executed up to a certain point, and then it moves forward and starts in going the correct way. So, and it can get away with this. It's very interesting and tricky stuff. But you remember we talked early in the course about the difference between using conditional moves and conditional jumps to implement conditional operations. And conditional moves can take place totally within the structure of this pipeline. But a conditional jump, if it's an unpredictable branch, the problem is it might go off executing and do a lot of wasted work, but even worse than when it gets back and has to restart, it takes a while to sort of fill up all the buffers in the system and get the whole thing running at full steam ahead. So that kind of finishes up then the way I describe it is, first of all, even, and stupid is probably too strong a word. Don't do, sort of keep in mind there's certain things that you should as a programmer be doing all the time. And they're not obvious, perhaps. And then begin thinking about tuning and getting some of the instruction level parallelism. And I describe it as for the machine, but as I said, pretty much all processors nowadays, it's a class of machines. And so these general techniques will work, that those ideas of changing the associativity, they'll work whether it's the ARM processor built into my cell phone or the x86 processor built into your laptop or one of the Shark machines. They all have the same general implementation structure. So these techniques will work across all of them. OK, that'll do us for today.
I didn't know that I was muted. Alright, counting operations. Testing the amount of time it takes to... Oh, it is 5:09. I am done with this shit. I'll come back to that later. I'm gonna take my break for dinner, and I'll be back around 6 probably. If not earlier. Probably finish dinner earlier. Oh, cool. Alright, I'll be back.